Hello, everybody. My name is David. I'm a grad student in the lab of Aaron Kapitulnik at Stanford, and I'm going to be talking about magnetism and infinite layer thin film nickelates. And to kick off motivation, let me draw your attention to the typical phase diagram of a cuprate superconductor, which has a striking difference from the phase diagram of a nickelate, because we don't see any antiferromagnetic modern insulating state in the parent compound, and actually no magnetism at all, because the nickelate is also known to have a spin glass state, which we once again not sure if there is some in the nickelate. So this is what I'm going to be talking today about. And okay, let me just try it without the. And there are some measurements of magnetism in nickelates. Namely, there is a μSR measurement that sees some sort of magnetism that onsets at the temperatures as high as 150 Kelvin, where they attributed some of it to spin glass, some to maybe some other sort of disordered magnetism. And quite importantly, they show that it is intrinsic because they can measure the magnetic volume fraction, which is close to 100%. And they say that it could be mediated by antiferromagnetic coupling between nickel spins. In contrast, the squid measurement show that there is some inhomogeneous ferromagnetic signal, which comes from a completely extrinsic reason, and nickel inclusions between the nickelate and the top capping STO layer. So today I'm going to try to answer some of the question about what is actually the origin of the magnetism in nickelates. And to do so, I need the right team. So let me introduce my collaborators, Martin and Jennifer from Harald Huang's lab, who grew the sample, and a nice photo of my PI, Aaron. Okay, so what do we actually measure? We measure something called magneto-optical Kerr effect, which is, let me teach you about it a little because I don't imagine everybody is familiar with what it is. It's defined as the change of the polarization angle of one reflection. And this angle is known to be proportional to magnetization in the sample. Why? Here's a simple explanation. When you shine light on the sample, this radiation shakes the electrons inside, which in turn, when they accelerate and decelerate, emit radiation. However, when we have a magnetic field, due to Lorentz force, their orbital motion is changed, and this leads to rotation of polarization, which is fully described by the simple Fresnel equations. And most importantly, the Kerr angle is proportional to the whole conductivity at the frequency of the light, which is why it measures magnetization in the sample. So this is the takeaway from the sample I would like you to remember for the rest of the talk. Okay, here's the data. First, we follow protocol of cooling the sample in a field, then turning the field off and measuring during the warm-up. And we repeat this with positive and negative field. And we see that there is indeed some sort of spontaneous magnetization in the sample, which onsets at about 80 Kelvin. However, it doesn't do it in a typical ferromagnetic-like way, something that where you would see a second-order mean field-like transition. Instead, it sets on very gradually. When we measure susceptibility, we first zero field cool down and measure it during the warm-up in field, and then we measure during the cool down in a field, and we see that actually the results are different, which is a known feature of a spin glass state where you have disordered interaction between magnetic moments. Furthermore, we can measure this magnetic signal as a function of time at fixed temperature, and we see that it slowly saturates in field and then slowly relaxes when the field is turned off, which is also known as aging, another hallmark of a spin glass state. However, most bizarre part is that after we measure the hysteresis at 10 Kelvin and cool the sample down and then measure the susceptibility once again during the warm-up, we see some sort of feature at the temperature at which we took hysteresis. So the system retains some sort of memory about what happened to it at a different temperature. This is also a feature of spin glass, which follows from its hierarchical state of the free space landscape. So all of this together lets us conclude that it's actually not the antiferromagnetism or ferromagnetism what is present in nickelates, but it's a spin glass. Magnetic interaction is disordered. And it's not a total surprise because in a similar compound of polycrystalline non-superconducting nickelate, the magnetization was also measured, and then they also see irreversible susceptibility, which is frequency dependent, and also has this memory effect and aging. And they also see this onset at the similar temperature at which we see around 80 Kelvin. Right. So Furthermore, when we tried to measure neodymium sample, we first observed similar results. We also saw spontaneous magnetization, irreversible susceptibility, aging. However, the same neodymium sample prepared on a different substrate, LSAT instead of STO, shows a dramatic reduction in this effect. The temperature is decreased from 70 to 14 Kelvin, and the magnitude of decay rotation from 6 microradian to about 1 microradian. So, given this data, what do we know about the origin of the spin glass state? Most probably, it comes from the process of topotactic reduction, where we remove apical oxygen from the perovskite phase. And sometimes there is some remnant nickel, sometimes not all of the apical oxygen is removed, which also changes coordination number of nickel and makes it magnetic. And also there could be other reasons for disorders, such as non-uniform doping or maybe strain from the substrate. And in fact, if you compare two neodymium samples prepared on STO and LSAT, you see that the STO one has much more vertical stacking faults. It has worse metallicity, as you can see from resistance data. So the red here is the LSAT sample, which has a lower normal state resistance and a higher TC of 15 Kelvin versus about 12 in the STO. Also, as I mentioned before, as seen in squid measurements, there are nickel inclusions on the interface between STO and capping layer, which could also be a reason for magnetic interactions. So do we see something like this in our data? Well, yes and no. On one hand, we do see some non-uniform signal. So this is a K-angle scan taken at 5 Kelvin, which once we warm up the sample, the background signal disappears, which we attribute to the spin glass. However, there are some bulbs of magnetic signal which still persist to a temperature much higher than the spin glass onset temperature. And this happens on a larger scale, so it could or could not be attributed to the nickel inclusions. We don't really know. Okay, so let me finally reiterate everything I said so far. So we observed spin glass state in the nickelate superconducting samples. We showed that this state actually onsets at temperature much higher than the critical superconducting temperature, in contrast in what we see to cuprates. However, we also shown that it depends a lot on the fabrication process, since the neodymium samples prepared on the LSAT has much lower freezing temperature. And I let finish by the open questions in this field, which I believe is that the next step would be to determine the origin of this spin glass, whether it comes from intrinsic reasoning, something like an RKKY interaction, or whether it comes from not imperfect fabrication conditions, and as they improve over time, the spin glass would diminish overall. Thank you for your attention.